Hello, I'm Gomes. I'm here to present my work, which is called Group Interactions Manager for Multiplayer Series Games. This work was done in conjunction, in the scope of my PhD thesis, and in conjunction with my supervisors, Professors Joao and Carlos Martinho. I'm going to start by introducing the team, namely by saying that nowadays learning support systems and adaptive learning systems are evolving to multiplayer serious environments, which aim to concurrently train and educate a massive number of people. Moreover, we are seeing a transition for the classic educational contexts to more gamified contexts, which apply elements from gamification to, in order to improve learning. So, what is the problem that we want to approach here? Here we want to check how can the collective ability of players be improved in a multiplayer serious game. Current approaches focus only on learning aspects of individuals. However, we want to instead focus on the collective and the interaction between the peers. Therefore, now that we had our vision in mind, we checked several related work from the education field. We checked that usual characteristics that were considered for the students and for serious game players are either their ability, so their previous knowledge, or the engagement, which is related to cognitive, to psychological, motivational aspects of the individuals. We also checked several interactions in student groups, namely that the most important ones that were considered for multiplayer serious applications were collaboration and competition. From these two, we also added the self-improvement dimension, and by self-improvement we consider to be the same task, the same individual task being performed concurrently by all of the elements, all of the grouped elements. So it's a way of integrating also individual tasks in a group-based application. The ability, we also checked that ability has an impact on the preferred interactions of the students. Namely that students with above than average prior knowledge tend to benefit more from competition and less from collaboration than actually students with lower than average prior knowledge when facing collaborative and competitive mixed scenarios. Finally, we checked the several work which focused on the promotion of social behaviors in games, and we observed that for incentivizing competition, we can use tasks which reward only one person in a group, so competitive reward tasks like tournaments or alike. And for collaboration, we can use tasks which either require other players' tasks, other people's tasks to be completed, or have to be completed by more than one person at the same time. Okay, now I'm going to actually present our model, Gimme. Our model is an iterative process which focuses on 3 steps. The first step being the creation and update of the learning states of each of the students. Then we organize the students into smaller groups and attribute to each group a group interaction profile, which is the interactions that need to be promoted in the group so that the students, collectively can learn, can improve their abilities. And then we combine for each group, and considering each group interaction profile, we build mechanics and actually incentivize the group interaction profile in-game. So, for the first step of our model, what we aim to do is that we have as I presented, we have these two characteristics, the ability and engagement. Ability can be acquired from the game by just considering the game score, so the score that has been accumulated until now for a player. And the engagement can be considered as in conjunction with the flow theory by using both the on-task time, the time that the student spends on a certain task, in conjunction with the task completion rate. So the percentage of the task that is completed by the student. If the student spends a low time in a certain task but completes a very big percentage of the task, then we can extrapolate in some way that the student is low, has low engagement. Oppositely, because the task is too easy. Oppositely, if the student completes a low percentage of the task but spends much time in that completion, then maybe the task is too difficult for the student, and so he must also be lowly engaged. Okay, this is the creation of the player learning state. Now, the actual organization step, how to organize the students into groups. So, how can we organize the players? We proposed a two-phase process. The first part is to compute several random group configuration possibilities, several random ways to divide the students, and also to generate randomly group interaction profiles for each of the groups. And this random process is supposed to be uniform. Okay. Next phase is to pick each of the students in each of the groups and try to predict their learning states when they are going to be faced with the interaction profile that we want to face them. So, in order to do that, we just see the past of the student, the past learning states, which are associated with past interaction profiles, and we use an algorithm called k-nearest neighbors for regression, which basically just allows us to find a prediction for the learning state when the student is going to be faced with the profile that we are testing. We do that for all the groups and average that over all the configurations, and we find an average learning state which is like a fitness of a group. Then we pick the group with higher fitness, and that's the group we want to consider, the configuration with higher fitness, and that's the configuration we want to consider in the second step. In the third step, we then want to combine mechanics, in-game mechanics, for each of the groups that we have on the second step, and each of the profiles that we want to promote. So, for this last phase, what we proposed was we have 3 buckets, one associated to a specific interaction, and with a plethora of tasks which have rewards according to those interactions. Then we combine several tasks from each bucket to create a composed mechanic, and that composed mechanic can actually then be adapted in terms of difficulty, to the combined state of the group, so that we have more suitable tasks in game. Okay, now I'm going to explain a little bit about the validation, about the evaluation process that we presented in our paper. Before exploring a more expensive route, as this is this is giving its first steps, we found it was more helpful to have simulation-based, agent-based simulations in order to test the core aspects of our model. So what we did was we tested multiple approaches for generating those configurations at the first phase of the organization process. We found out that the suitable algorithm was to compute a random configuration size, then have 2 students in each group, and distribute the rest of the students randomly throughout the groups. And so, this way we could generate our random configurations. Then we compared the amount of generated samples, and we checked that for our simulations 100 samples were suitable. Then we compared the amount of nearest neighbors in our KNN algorithm, and we checked that 5 nearest neighbors was a suitable parameterization for the algorithm, so that it could perform accordingly. One thing that I didn't say was that in our tests we used kind of a class size of an average class size in terms of I think it was American class size, so an average American class size. It was around 23 students. What we did to test the algorithm itself was to compare the average ability increase of all the students along each iteration of the algorithm and their engagement, at least the way we modeled it in the simulation. We modeled them in the simulation, and we compared them to both a random strategy, which was like a strategy that always returned random configurations without acknowledging our group organization process, and it's a strategy usually considered by professors when they don't know the students, and we compared these 2 strategies, our and the random, with the optimal strategy that would occur if we had our process know exactly what if we knew exactly what profiles to incentivize so that the ability of the students could improve maximally, optimally. We have seen that our strategy deviated much less from the optimal strategy than the random strategy, which proved that it was the potential of our method. The last thing that we checked was, I didn't show the engagement because the way we modeled the students, it was very similar, the chart, the plot. Then we compared the average profile to preference differences. Here preferences was like a construct of our simulation, which was like for each student the profile that allowed him or her to evolve in the best way. And so when we compared our strategy, the optimal strategy and the random strategy, we have seen that our strategy variation was lower, and that the distance was also lower than the random strategy. Okay, to conclude my presentation, what have I described? Firstly, I described our approach. Then I presented how we validated the core aspect of our approach to simulations. In the future, what we aim to do is to further improve some aspects of our model, namely the way we consider the adaptation space in order to have maybe more complex interactions than the ones that were described in related work. We also aim to test this in a real scenario, so with real students, when we have in a more user testing scenario, and a smaller scope improvements can include instead of generating random configurations, having an evolutionary process which consider the test states and try to not spread out the whole interaction space in just the spaces which are more suitable for a specific state of the application, and using a grid when storing past profiles in order to cover the interaction space with a less number of samples, a lower number of samples. Okay, thank you very much for your attention. Some questions? This one?
Thank you for the presentation. I would like to ask you, you have some metrics like the game score and the task, the time spent on the task and some other things, and then how do you know that these metrics actually map to the specific abilities, competencies that you have in your study, like communication, what is it, collaboration, and
yeah, it's competition, collaboration, and
collaboration. So
self-improvement.
Yeah. Me coming from the field, knowing the importance of statistical models and being able to have reliable models, I cannot really understand how you ended up with these metrics and this kind of models. So if you could explain it.
On one hand, ability we thought as the knowledge that is obtained by the student until now. So for that we can just extract from the game the score, and that gives us a pretty fair approximation, or pretty good approximation of the state of the player until now. The engagement, we thought more about the flow theory, which says that in order for a student to, or the game flow theory, in order for a player to maintain high engagement, the difficulty of the task has to be adapted to his state, to his. And so we try to convey that idea with the on task time and task completion percentage.
A similar question, you had this distance plot, distance to the optimal strategy, and I just did not understand how do you know what is the optimal strategy in this case?
Yeah, because we had simulations, we considered the optimal strategy to be like the process that we have, like generating a considerable number of samples too, but instead of using KNN, using the predictions, we actually computed the exact future states. So it's like the model knew the future states and could act exactly with those future states instead of providing an approximation, a prediction. So it's a way to check, to validate the prediction part of the group organization process.
Okay, so thank you for your presentation. So we can start with the second one. The title is Portability of Game Software Components, and the presenter is Bimanual.
Okay, welcome. I'll start this presentation. You already heard my name. I'm from the Open University in the Netherlands. This is, the problem we're trying to address is in the research, and the project that funded this research. Basically, if we want to port, let's say, components, functionality between all kind of platforms, target platforms, development environments, we end up with really a lot of stuff we need to account for. So basically what we could do is develop only for Unity, but then it won't work in anything else. So we can develop it for iOS, it won't work on Android. So basically what we tried to do was to, well, tackle this problem and make a software architecture that allows easy porting between all this. I'll first start a little bit with an introduction on the Vegt project. It has recently finished, but it has, due to its size, a considerable afterlife. So that's normal with the EU project, but this one is, well, it has some special things in its afterlife. Then I'll introduce the architecture we devised to tackle the problem. Basically, well, we wanted to design a highly portable architecture for components, and it should also be easy to use, and it should save game companies, serious game companies, money, so it should be easy to integrate, etc. Then I have some slides about portability, and finally, well, if I'm quick enough, questions, hopefully. So Vegt was an EU Horizon 2020 flagship project, basically to boost the serious game industry in the EU, which is highly fragmented. Well, it's not dominated by large companies, but small ones, so a few employees at most, at least one we encountered. There are no big serious game companies with thousands and thousands of employees, at least not in the EU. We focused on components implemented pedagogical functionality because, well, the project was a combination of commercial parties or educational institutions, game studios, serious game studios, and universities, and some other types. Basically, pedagogical functionality like, well, self-assessment, but also real-time emotion recognition, natural language processing, able to extract emotion from text, that kind of stuff. We created components in two flavors. Well, one is server-side, basically applications, the big Java stuff that runs on a server, exposes a web interface or service. And client-side. And client-side components means that they are actually integrated into the game itself. So it's not running alongside, it's integrated into the game itself. Client-side is either, well, the client for server-side or standalone. It depends a bit on if there is heavy computation involved or not. We also validated the components. We built 7 full-fledged games, which had at least one, and in most cases many more components integrated into it. We created a complete chain from component developers, game studios creating actual games for their clients within the project. Clients like Randstad France, who needed a game to teach people about how to behave during job interviews. So basically we created games that also have an afterlife that can be used after the project by the companies ordering them. So we had a complete chain, and we were able to use, let's say, the clientele from Randstad France and some educational institutions, so students, as end users for these games, and validate that the components inside were working as expected and improving learning and that kind of stuff as expected. Most games had a focus on entrepreneurial skills, damn, difficult word, and employability, so also useful. Components are available, I think most are free, around 50 of them at gamecomponents.eu. Most of them an Apache 2 license attached, so basically you can do anything with it, sources are there. We created 7 complete games, and well, we used over 1,500 users to validate the stuff. This is a screenshot of an actual game created by a London-based company called PlayGen. It's about managing not a football team, but a sailing team, and basically that needs some decision making on some social stuff like conflict management, that kind of stuff. You put think 7 or so people onto a small boat, and they have to be there for maybe 2 weeks or a month sailing. And they shouldn't quarrel, so there is some conflict management involved, and well, all kind of stuff. So. This is the architecture, or at least a slide about the architecture we devised. We based it on software design patterns. Saves a lot of meetings because you're not starting right away about the code, but you just choose a number of design patterns, software design patterns you want to use, and then find a good implementation. Also makes it easy to port it to another language. Basically, you find the correct implementation. That's already hard enough sometimes, but you find the correct implementation, and you only need to write the remaining glue in between. Portability, well, it was by design. We designed the architecture so it was easily portable, but we also have some rules attached. Things not to do. I'll visit them later. Basically, portability was across development environments, so we didn't want Unity-only components. Basically, they suck once you don't use Unity, and then they're totally worthless. So we also wanted to support Xamarin, Visual Studio. We also tried Xenco, which is an open source, freely available Unity lookalike. Game engines, well, Unity of course, but also monogame, Kurvers 2D, which is a JavaScript one, so it's still on C#. Target operating system, we want to be able to deploy to all the platforms using a single code base, so not a specific version for Xamarin or for monogame, just one code base, and be able to deploy it. We deployed it to Windows, OS X, or Mac OS, it's how it's going to be called, Android, iOS, but also Windows Mobile, and browser even. We tried some WebGL, but it was very slow in compiling, but it worked. Target hardware, well, desktop, mobile phone are the obvious choices. We didn't include game consoles because they have often, the development licenses are often very costly, and none of the serious game companies was able to pay that kind of license fee. So, programming languages, C# was the main development because they mostly all liked, of course, Unity. But we also did TypeScript, which is a typed version of JavaScript. It takes out a lot of runtime errors, which you get if you deploy JavaScript. It compiles to JavaScript, but it has during compile time it does type checking, and it has also all the object-oriented constructs that C# has. So it's easy porting. The syntax is slightly different, but we also did Java, and the architecture is also available in implementation in C++. Basically, it was designed to be used in the game and not overtake it. So we don't want the component developers to make nice decisions about things that are up to the game developer. So basically, when the first components were available, we saw that, component developers just entered the path where files should be saved. Worked nice in Unity, worked nice on Android, but the path just wasn't there on iOS. So basically, that kind of stuff, like where files are stored and how they are stored, is not up to the component developer, but is for the game developer. He also has to adjust his project, his permissions and that kind of stuff. So we managed to create the that fast. Okay. Well, the integration code is also shared because it doesn't have any user interface. It's easy for that's sweet, and it looks a bit like a container. And basically what you do inside the container is up to you. You can make a guest room, an office, swimming pool, cocktail bar. You still know how to handle it. You can still load it onto a truck and drive around with it. I would remove the bottom, but that's about it. So this is how it looks like. In blue is the game engine, all the parts. Red are the stuff where you don't want to go. And in green is is the architecture and the payload. Basically in white, the bridge there in between is the part where we supply functionality. So we use interfaces for it, so we can implement them in game code and we can safely call them from within the payload. Like a logging interface, it's a single method log. Game developer implements it, sends it to wherever he likes it. And then the payload can just log diagnostic data, and it doesn't know where it ends up, but it's not up to him or her to decide. So, portable across multiple dimensions, but it is a sparsely filled matrix. If you have a Java-based component, well, you can't run it on iOS because there is no Java engine available, so there are some no-go areas. We are dependent on what the game development environments like Unity or Xamarin support as output or as target platform. We, as part of the research, reported a component that matches player performance to game difficulty, fairly automatic. It doesn't need to know what it's adapting, it just needs labels like easy, medium, hard, and it will automatically adjust based on just a win-lose boolean and a time on task, and it will start rating the things it can adjust to the player performance. Player performance, if you plot it, you have its learning curve, so it's pretty easy to use, and we ported it to, deployed it to Mac, Windows, using Visual Studio and then Unity, Xamarin, iOS, Android, Windows Mobile, and even to a browser, but that took pretty long to compile. I don't know, this is a Unity issue, I guess. We translated it to TypeScript. Basically, we renamed the files to TS, and then we got a lot of errors. Mainly, the method signature is slightly reversed, and there are some issues with data types, and the rest is pretty much the same. We integrated it into CoG 2D JavaScript game engine, implementing a board game, and well, it happily runs. And we also imported it to Java. And we integrated it onto a server-based game development environment called Imago, which is developed by UNL. And then it happily ran on the server side, so it ran inside a big Java application. But because the components really don't know and don't need to know where they are running and on which hardware and that kind of stuff, basically it just ran. The only thing we had to do to integrate it nicely into Imago was a small layer on top, so it was recognized as all other components that this system has, and based on that it could create editing pages and configuration pages and that kind of stuff. So basically we translated this into this, and we didn't believe in wrapping up, let's say, Java and run it in C# or the other way around, so that's nice, but it's never mainstream, and it isn't portable often, so basically we only have to port between the languages. The architecture, so the underlying base classes are already ported, so you only have to port your own payload. So, well, slightly over time, I guess. I still see a 5, but that's accidental, I guess. Basically, if you have any, if you're interested or have something to share, well, visit gamecomponents.eu. I would say, well, my email address is probably also in the paper, so if you have questions, just mail them.
Thank you for your comment. Some questions?
Awfully quiet.
No,
Okay.
I have general questions about Rage. Rage is ended now, right?
Yes.
What about the future of gamecomponents.eu, the marketplace?
The typical EU project has a 3-year afterlife in which stuff is it has to be kept alive. The Rage project has some special issues because of the size. It has some special, but I'm not the project manager, but it has a longer commitment, so there are all kinds of stuff.
Okay, but there is some association or something like that that can...
Yeah.
Okay,
yeah.
in this way.
Yeah.
Okay.
Yeah, it was it was the EU that said we had to do it. So, but it's just mainly because the size of the project that the afterlife is longer than usual.
Okay.
Yep.
Thank you.
Okay.
Last presentation by Nuria Pena Perez, and the title is Exploring Motor Behaviors in Bimanual Interactive
Do you need a
Games.
pointer? Just putting forward.
There was my bag here. Someone take it for her. My bag with the. It was on the table.
Back.
Yes, my bag with the stuff of the conference. Oh. Thank you. Sorry, no problem. Okay, please.
Okay, thank you very much. So I would like to start this presentation by discussing the main motivation and application of this work, which is stroke and rehabilitation. So stroke is the interruption of blood supply to the brain. It can happen because of the rupture or because of the blockage of a blood vessel in the brain. And in any of these cases, there is a lack of oxygen and nutrients. So the cells run in the area where stroke happened, they die, and several functions can be affected depending on the area where it happens. One function that is usually affected is motor control. If the stroke happens in one side of the brain, in one hemisphere, the opposite side of the body is affected and suffers from general weakness. So as you can see in this video, this patient is helping with her stronger side of the body, the weaker side, in order to perform this exercise. This problem is known as hemiplegia. Why is it important to contribute towards stroke and rehabilitation? Well, every 2 seconds, someone suffers from stroke, and there will be 70 million survivors by 2030. 2/3 of the survivors suffer from motor impairments, and this loss of mobility affects their quality of life, their ability to work, and their mental health. So there is an urgent need to develop highly efficient, safe, and affordable therapies. How is therapy usually being given? Well, conventional therapy is given in a one-to-one basis. There is direct physical contact between the therapist and the patient. The therapist guides the patient in controlled exercises, and then follow-ups how recovery is happening. Robotic therapy is currently being used together with conventional therapy because these robotics devices can guide in more controlled movements. They can relieve the therapist in this physical workload, and they can also record the physical parameters, the movements of the patient, so this makes it easy for the therapist to actually follow up how recovery is happening. But the problem is that therapy is quite exhausting for the patient. You need hundreds of repetitions of the same movement in order for recovery to happen. So games have proven to be quite useful for rehabilitation. They can engage the patients. If they are used with simple devices, they can allow for practice outside of the clinic, and they can still record the movement of the patient and how are they recovering, so that the therapist can still follow up their improvements. This is a game, a social game that was developed for therapy. As you can see, the patient would play in the hospital together with the therapist. When the patient was outside of the clinic, they could still play with a family member or with a friend. What happens? Well, not every game is equally useful. The task is very important. The task needs to promote recovery, and something quite relevant is that effort from the patient side is required. If the patient is not actually moving, if there is a slack in behavior, then the motor system won't improve. So how can we design tasks that are actually useful for recovery? Well, what these people did with this game, which is called Balloon Buddies, is that they defined a concept which is called, they call local redundancy. So they imply that activity of both participants playing was definitely required in order for the task to be successful. So in that case, each participant is taking control of inflating one of the balloons, so that if one of them is actually slacking, then the plant won't be leveled and the girth will fall off the plant, which usually so happening in the video. However, something that is quite good is that there are many different strategies in order for the plant to be leveled. So if the patient is actually not being quite successful in controlling the inflation of the balloon, the therapist can de-inflate their balloon so that the plant is still level even if not all the stars are being collected. So this allows for a certain leveling of the scales, which is interesting because it keeps the patient motivated. Another thing that we thought would be interesting for a task for rehabilitation was to work with bimanual tasks. Bimanual coordination is very relevant for daily life activities. We need it for tying our shoelaces, opening water bottles, sweeping the floor. And in MEP patients, as you saw in the first video, patients can use one stronger side in order to help the weaker side. So for example, that guy might be supplying most of the force with the stronger hand, but the weaker hand would still be contributing towards just maybe guiding, but still putting an effort, so still working. So for this project, we thought we wanted to design a task that was specifically thought for bimanual coordination, and since it is still unknown how or bimanual coordination works, how healthy motor strategies arise in this type of task, we wanted to develop a pilot study in order to explore these patterns of coordination. So, what task did we design? Well, we designed a task which was controlling one single game object, which was a rocket, with 2 fingers. So basically, the participants, by pressing each of the triggers in an Xbox controller, they control the rocket. You can imagine that the rocket in its side has one motor, so by pressing with one of the fingers you give energy to one of the motors, and by pressing with the other you give energy to the other motor. So if you press the triggers by the same amount, then the rocket moves forward. However, if you press one trigger more than the other, if you give more pressure, then the rocket will actually turn. So what is important here is that this difference between the 2 inputs is what actually is going to make the rocket turn by one amount of the other. So there are many different strategies in order to move the rocket in the same path, but still be successful. So we designed a virtual task in Unity, which was just tracking this circuit that you can see in the screen. So first one circle, then the other circle, and then arriving to the finish line. So a very, very simple task. And for our pilot study, we asked 10 healthy adults to play for 10 rounds of the game. And we recorded both the pattern of pressure that they exerted in the triggers and also the rocket-related variables. So the position, the velocity, and the time at which everything happened. So this can be a bit confusing right now, but this is the data for 3 specific participants, player D, J, and H. So these graphs, they correspond to the input patterns. So the red is the left hand pressure, and the blue is the right hand pressure. And then the other graph, it corresponds to the player's trajectory, which is in yellow, and the ideal trajectory that they have to follow, which is in black. So as you can see, with different input patterns, each of the players obtained a different output trajectory. Not all of them were equally successful. As you can see, player H had some issues to actually track the trajectory, and in order to characterize this better, we defined 2 different metrics. We first defined an error metric, which was just calculated as the distance between the player's trajectory and the ideal trajectory that they had to follow. And then in order to characterize their inputs, we used a metric which is the smoothness, which is calculated as the path length of the frequency spectrum of the signals that they were in their input patterns. So, as for example, signals that have a higher frequency component, they will have a longer path length, and therefore a worse smoothness metric. However, patterns that are more smooth, that seem more continuous, like for example for player J, these people will have a better smoothness value, which is closer to 0 error. So as you can see in here, player D and player J, they have completely different inputs. Player D seems to be moving their fingers in a very intermittent manner with a very bad smoothness, while player J seemed to be using a more continuous, smooth strategy, but they both actually managed to track the trajectory quite good. So we were wondering, why do players choose one strategy or another based on this smoothness metric? So in order to further investigate this, we plotted the smoothness against the error. So in this graph, you can see lower values correspond to more continuous, better smoothness, and higher values they correspond to worse smoothness values. Each of the circles represent one participant, and the color represents their perceived expertise in Xbox controller or games in general. So just by visually inspecting this figure, we could see that there are 3 participants that seem to have a very, very bad smoothness measure, and in general, all the other participants seems to be more continuous in their control. And what was interesting was that the people who actually use this more intermediate strategy in general achieve a lower error. So humans, it's known that we minimize the cost function based on our error and our effort. So what we hypothesized is that in general a more continuous strategy can be more difficult because it allows you to not account as well for what's going to happen in the next time point. While if you are pressing the triggers like this, it allows to account better for possible instabilities. And these participants were more intermittent in control. They actually complained that the triggers were squeaky, that they were tired after 10 rounds of the game. So we thought that these people were actually putting more effort in the task, but they all achieved a lower error. So we think that the reason why participants will choose one strategy or the other in terms of the smoothness will depend on how familiar or comfortable they were with the task and how much effort they actually wanted to put in finishing it. As you can see, the player with the lowest error and actually a very good smoothness value was player J, which was the only one that considered himself an expert in the task. So this is our hypothesis, but of course we still need to put some further work in this. So first we would like to recruit more participants so that this is not only an analysis based on visual descriptions, but in actually analytical and statistical testing. And we also would like to increase the number of game rounds, because we hypothesize that once players are more comfortable with the task, they would actually start moving from the more intermittent strategy to the more continuous one, just focusing on minimizing their error once they feel they can actually achieve it. But we will need more round of the game for this. Secondly, we would like to model the strategy of the participants. So as I mentioned, we do minimize cost function based on error and effort terms, and the coefficient for each of these terms will tell us how are we actually penalizing each of these terms. However, for bimanual coordination, these models are still unknown. Which model is going to be best for data is still unknown. So we will need to try, and we are going to do our work based on 2, based on optimal control. Optimal control models, we consider that we are using only one cost function, so the 2 hands will be working within the same system, assuming that through interhemispheric communication, one hand knows the position at all times of the other, and all of the force interaction is well known. However, we can also use a model based on game theory. In this case, each of the hands would have their own cost functions. They would consider separate agents, and there won't be perfect knowledge of the entire system. They would have to perceive what the other hand is doing. And the third thing we would like to do is to do this further experimentation, but with actual rehabilitation devices. So this company called Gripable, they manufacture these gripping force devices, which also detect the exact level of pressure that you are putting. But by repeating the experiment with these devices, we know that the data for healthy participants can be then further compared with actual data for patients, so that we once establish this ground truth of what are our motor strategies in this type of task, we can compare it in the future with data for patients and then keep working on developing therapies for them. And this was all. Thank you very much for listening. If you need to contact me, thank you.
Some questions?
Thank you. I think that I missed one significant point. You talked a lot about how players become better if their moves are smoother.
Yes.
But from a medical point of view, does being smoother at playing the rocket game mean that you are better? Does it mean that you are actually rehabilitated?
Yes, so that's a very good question, and I didn't mention, but smoothness is a metric that was developed taking into account that in general motor control is classified as a skill when it is smoother. So if you think in like childs moving their arms, for example, there is a lack of actual control. That means that the movement is performed in bursts. And once you learn how to smoothly control, then that's considered as a more skilled movement. So ideally, you could use this to track, the smoother the person becomes, then the more skilled they are at the task. In the case of the rehabilitation devices, by pressing, for example, it is quite difficult for the patients to actually release. That's quite difficult. So if you notice that they are managing to actually press and then decrease the pressure in a smooth manner, then that means that they are improving.
So, can I have a follow-up question? So, in that sense, at some point, if one patient gets used to one difficulty level, let's say, it would be good to have more difficulty or extremely difficult.
Yes, definitely. So, and that's why we actually did this specific type of task, the driving one, because the task is not programmed using Unity physics, it's programmed using a full dynamic model based on a differential wheeled robot control. So that means that, for example, you could affect any of the parameters of the vehicle, like for example the friction of the wheels, you could affect the mass, and by that you can give many different types of difficulty levels that you can also show on the screen, like a banana, skin, and then the player would have to adapt to those different situations.
Yeah, really interesting talk. So it was, I might have missed it, but so when you're classifying the player strategies, so there's some that aren't smooth and some that are smooth.
Yes.
And so I think I missed it. How does choosing in healthy adults that distinction? How does that help with the stroke treatment?
You mean how do we translate this knowledge to future?
Yeah.
Yeah.
So in the future work,
So
how would that?
exactly, that's what we don't know. Since the problem is that right now, for this specific task, there is still not enough work in modeling and understanding how this bimanual control works in healthy subjects. So what we hope is when understanding how everything works in healthy subjects, then we can establish some groundwork so that then we can better understand how stroke patients can compare to that.
Okay.
Last question.
Question also about the healthy people. Did you take into account that eye-hand coordination? Basically, if I turn my monitor 90 degrees and try to move my mouse, it's terribly difficult. So I get all the wrong moves, like I go totally off scale. So and it improves over time for most people, but not for all.
I don't know if I understand what you mean, like for experimental conditions between the same type of people, or. So what we did was to give a practice trial for this. So for us what is interesting is how do they specifically track that specific path. So what we did is before the actual experiment, before the 10 rounds, we allowed them to play in just an empty screen, just controlling the rocket, so that they could definitely feel comfortable with controlling the parameters, making the rocket turn. And then once they actually played with the actual path, then they could choose whatever strategy they felt more comfortable with. And yeah.
We have that?
Okay, yes, just one. Yes.
We saw a graph, a plot that you have.
Yeah.
So this is the final scores. Is this like cumulative average scoring of each player?
Yes. This is the mean error, and then is the average across the 10 trials. So what I did was to actually see first if there were differences across trials, because I expected some improvement along trials. But in general, no one actually improved. But again, this is something that I will need to recruit more people and then more trials so that I could actually check if there are some differences, and then maybe consider only using the last set of trials for each of the people to recreate the scraps.
So did you maybe consider any demographic differences between the players, like a game experience?
So that's that's a very good question. But all of these 10 subjects were coming from CBT in intelligent games and game intelligence. They were all between 21 and 25 years old. So like demographic were like very With a larger study, that's definitely something to consider, especially if there is a wider age range or something like that.
Okay, thank you again.